In this video, the following topics will be covered: rule-based classification, model evaluation and selection, metrics for evaluating classifier performance, techniques to improve classification accuracy. Rule-based classifier uses a set of if-then-else rules for classification. An if-then rule is an expression of the form R1, that is rule 1, if age equals sign youth and student equals yes, then buying a computer equals sign yes. Here the if part of a rule is rule antecedent or precondition. Then part of a rule is known as a rule consequent. The rule antecedent, the condition consists of one or more attribute tests that are logically evaluated. The rules consequent contains a class prediction. Accuracy and coverage. The rule R can be assessed by its coverage and accuracy. Given a tuple X from a class labeled dataset D, let n covers be the number of tuples covered by the rule R. N correct be the number of tuples correctly classified by the rule R, and dataset D be the number of tuples in dataset D. We can define the coverage and accuracy of R as coverage of R equals to n covers divided by the dataset D. Accuracy of R equals to n correct divided by the number of covers. If a rule is satisfied by X, the rule is said to be triggered. If more than one rule is triggered, we need the conflict resolution strategy to figure out which rule gets to fire and assign its class prediction to S. Size ordering and rule ordering. Size ordering means assigns the highest priority to the triggering rule that has the toughest requirements, where the toughness is measured by the rule antecedent size. Rule ordering is prioritize the rules beforehand. The ordering may be class-based or rule-based. Class-based ordering means classes are sorted in order of decreasing importance, such as by decreasing order of prevalence. Rule-based ordering. The rules are organized into one long priority list according to some measure of rule quality, such as accuracy, coverage, or size. When rule ordering is used, the rule set is known as a decision list. When there is no rule satisfied by X, a fallback or default rule can be set up to specify a default class. The default rule is evaluated at the end. Rule extraction from a decision tree. Decision tree classifiers are a popular method of classification. They are known for their accuracy. Decision trees can become large and difficult to interpret. In comparison with the decision tree, the if-then rules may be easier for humans to understand. To extract rules from a decision tree, one rule is created for each path from the root node to a leaf node. Each splitting criterion along a given path is logically ANDed to form the rule antecedent. The leaf node holds the class prediction, forming the rule consequent. Classification rules from a decision tree. The decision tree, as shown in the figure, can be converted to classification if-then rules by tracing the path from the root node to each leaf node in the tree. A disjunction, that is logical OR, is implied between each of the extracted classes. Because the rules are extracted directly from the tree, they are mutually exclusive and exhaustive. Mutually exclusive means that we cannot have rule conflicts here because no two rules will be triggered for the same tuple. Exhaustive means there is one rule for each possible attribute value combination, so that this set of rules does not require a default rule. Therefore, the order of the rule does not matter, they are unordered. Logical OR is implied between each of the extracted rules. Mutually exclusive and exhaustive. Mutually exclusive means cannot have rule conflicts here because no two rules will be triggered for the same tuple. Exhaustive means there is one rule for each possible attribute value combination. Model evaluation and selection. Data from the previous sales to build a classifier to predict customer purchasing behavior. An estimation of how accurately the classifier can predict the purchasing behavior of the future customers, that is, future customer data on which the classifier has not been trained. Different methods to build more than one classifier, and now wish to compare their accuracy. Number 1. Metrics for evaluating classifier performance. Holdout method and random subsampling. Third, cross-validation. Fourth, bootstrap. Fifth one, model selection using statistical tests and significance. Metrics for evaluating classifier performance. It presents measures for assessing how good or how accurate the classifier is at predicting the class label of a tuple. Consider the case where the class tuples are more or less evenly distributed, as well as the case where the classes are unbalanced. They include accuracy, sensitivity, specificity, precision, and F1. Note that although accuracy is a specific measure, the word accuracy is also used as a general term to refer to a classifier predictive ability. Using training data to derive a classifier and then estimate the accuracy of the resulting learned model can result in misleading, over-optimistic estimate due to over-specialization of the learning algorithm to the data. The formulas are given for the measures. Accuracy equals to Tp plus Tn divided by P plus N. Error rate is given Fp plus F1 divided by P plus N. Sensitivity Tp by P. Specificity Tn by N. Precision Tp by Tp plus Fp. And F1 score 2 into precision into recall divided by precision plus recall. Then F beta also given 1 plus beta square into precision recall divided by beta square into precision plus recall. True positive, this refers to the positive tuples that were correctly labeled by the classifier. True negative means true. These are the negative tuples that are correctly labeled by the classifier. False positive, these are the negative tuples that were incorrectly labeled as positive. False negative, these are the positive tuples that were mislabeled. The confusion matrix is a useful tool for analyzing how well your classifier can recognize tuple of different classes. TP and TN tells us when the classifier is getting things right, while FP and F1 tells us when the classifier is getting things wrong. The confusion matrix for the class of Bayes computers in dataset DS and Bayes computers equals to no, where an entry in row I and column J shows the number of tuples of class I that were labeled by the classifier as class J. Ideally, the non-diagonal entry should be 0 or close to 0. The sensitivity and specificity measures also can be used. Sensitivity is also referred to as the true positive rate. Specificity is the true negative rate. These measures are sensitivity equal to Tp divided by P, that is total number of positive in the denominator. Specificity equal to true negative divided by total number of negative. It can be shown that accuracy is a function of specificity and sensitivity. A confusion matrix for medical data where the class values are yes and no for a class label attribute. It's shown on the table. Confusion matrix for the class label classes cancer equals to yes and cancer equals to no. The classifier is 19 divided by 300 equal to 30%. Specificity equals to 19.56%. Classifier's overall accuracy is 96.50%. Thus, we can note that although the classifier has a high accuracy, its ability to correctly label the positive class is poor given its low sensitivity. These measures can be computed as precision equals to Tp divided by Tp plus Fp, recalls equals to Tp divided by Tp plus Fn. Alternatively, there is another way to use precision and recall is to combine them into a single measure. And this is the approach of the F measure. They are defined as F is equals to 2 into precision into recall divided by precision plus recall, where this is a non-negative real number. F measure is a harmonic mean of precision and recall. In addition to accuracy-based measures, classifier can also be compared with respect to the following additional aspects. One is speed, robustness, that is ability of the classifiers to make correct predictions. Scalability refers to the ability to construct the classifier efficiently or given large amounts of data. Interpretability refers to the level of understanding and insight that is provided by the classifier. The holdout method, the largest data set is randomly divided into three subsets: training set, validation set, and test set. Random subsampling, which is also known as Monte Carlo cross-validation, as multiple holdout or as repeated evaluation set, is based on randomly splitting the data into subsets, whereby the size of the subsets is defined by the user. The random partitioning of the data can be repeated arbitrarily. In contrast to full cross-validation procedure, random subsampling has been shown to be asymptotically consistent, resulting in more pessimistic predictions of the test data compared with cross-validation. In K4 cross-validation, the initial data are randomly partitioned into K mutually exclusive subset pools D1, D2 up to Dk, each of approximately equal size. Training and testing is performed K times. In iteration I, partition Di is resolved as a test set and the remaining partitions are collectively used to train the model. That is, in the first iteration, subsets D2 to Dk collectively served as training set to obtain a first model which are tested on D1. The second iteration is trained on subsets D1 and to Dk except D2 and tested on D2 and so on. Unlike the holdout and random subsampling method, here each sample is used as the same number of times for training and once testing purpose. Leave one out is a special case of k-fold cross-validation where k is set uh, to the number of initial tuples, that is, only one sample is left out at a time for the test set. In a stratified cross-validation, the folds are stratified so that the class distribution of the tuples in each fold is approximately the same as that in the initial data. The bootstrap method samples the given training tuples uniformly with replacement. Each time a tuple is selected, it is equally likely to be selected again and re-added to the training set. For instance, imagine a machine that randomly selects tuples for our training set. In sampling with replacement, the machine is allowed to select the same tuple more than once. A commonly used is the .632 bootstrap method. Some other techniques to improve the classification accuracy: ensemble method, bagging, boosting and AdaBoost, and random forest. Ensemble for classification is a composite model. Individual classifier vote and a class label prediction is written by the ensemble method on the collection of votes. Bagging, boosting, and random forests are examples of an ensemble method. Ensemble combines a series of k-learned models M1 to Mk with the aim of creating an improved composite classification model. An ensemble needs to be more accurate than its base classifier. For example, consider an example that performs majority voting. That is, given a tuple X2 classifier, it collects a class label prediction returned from the base classifiers and outputs the class in majority. The base classifiers may make mistakes, but the ensemble will misclassify X only if over half of the base classifier are in error. Ensembles yield better results when there is significant diversity among the models. The bagging method. Given a dataset D of tuples, bagging works as follows. For iteration I equals 1 to k, a training set Di of D tuples is sampled with replacement from the original set of tuples D. The term bagging stands for bootstrap aggregation. Each training set is a bootstrap sample and sampling with replacement is used. Some of the original tuples D may not be included in Di, whereas others may occur more than once. A classifier model Mi is learned for each training set Di. To classify an unknown tuple X, each classifier Mi returns its class prediction, which counts as one vote. The bagged classifier M counts the votes and assigns a class with the most votes to X. Bagging can be applied to the prediction of continuous values by taking the average value of each prediction for a given test tuple. The bagging algorithm creates an ensemble classification models. D is a dataset training tuples, K number of models, a classification learning scheme. Ensemble output is a ensemble, a composite model. Method is I equal to 1 to k that create k number of models, create bootstrap sample DA by sampling D with replacement, use DI and the learning scheme to derive model MI. To use the ensemble to classify a tuple X, let each of the K models classify X and return the majority vote. Boosting method. A patient have certain symptom. Instead of consulting one doctor, assign weights to the value of or worth of each doctor's diagnosis based on the accuracies of the previous diagnosis they have made. The final diagnosis is then a combination of the weighted diagnosis. In boosting, weights are also assigned to each training tuple. A series of K classifiers is iteratively learned. The final boosted classifier combines the votes of each individual classifier where the weight of each classifier vote is the function of its accuracy. The boosting algorithm is shown on the screen, and D is a set of class level training tuple. K is the number of rounds, and classification algorithm learning scheme. Output from this algorithm is a composite model. Random forest. Given two classes of data, their data class are imbalanced if the main class of interest is represented by only a few tuples. The class imbalance problem is closely related to cost-sensitive learning. In medical diagnosis, for example, it is much more costly to falsely diagnose a cancer patient as a healthy. A false negative error could lead to the loss of life. Other applications involving class imbalance data include fraud detection, detection of oil spills from satellite, radar images, and fault monitoring. Traditional classification algorithms aim to minimize the number of errors made during classification. Let assume that the cost of false positive and false negative errors are equal by assuming a balanced distribution of classes and equal error cost. Although the accuracy measure assumes that the cost of classes are equal. For example, presented sensitivity or recall and specificity, which help to assess how well a classifier can predict the class label of imbalanced data. Approaches for improving the classification accuracy of class imbalance data. Number one, oversampling. Number two, undersampling. Number three, threshold moving. Number four, ensemble technique. The first three do not involve any changes to the construction of the classification model. Oversampling and undersampling change the distribution of tuples in the training set. Threshold moving affects how the model makes decisions when classifying new data. Both oversampling and undersampling change the training data distribution so that the rare classes were well represented. Oversampling works by resampling the positive tuples so that the resulting training set contains an equal number of positive and negative tuples. Undersampling works by decreasing the number of negative tuples. It randomly eliminates tuples from the majority class until there are an equal number of positive and negative tuples.